So picture this. You download a perfectly working machine learning project from just last year.
Oh, setting yourself up for heartbreak already.
Right. You're excited, you're ready to dive in, you run the code, and immediately, just right out of the gate, you get hit with this massive wall of red text.
The dreaded stack trace.
Exactly. It says, attribute error. Module NumPy has no attribute bool. So you message the friend who actually wrote the code, and they hit you with that absolute classic infuriating line.
Let me guess. Well, it works perfectly on my machine.
Yes, the classic. And you have the exact same code, right? Not a single line is different. But, well, over the last year, NumPy 2.0 came out and removed some deprecated aliases like np.bool.
Yeah, they cleaned house.
So your system has the shiny new latest version of NumPy installed, but your friend's system, the one where the code actually runs, has the older version. Same exact code, completely different results. This is the dreaded environment drift. And before we unpack how to stop this invisible killer from ruining your life, welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
Which is, the core reason we are tackling this specific bottleneck today. I mean, you really cannot build real-world applications if your foundation just completely collapses the moment you move it to a new computer.
Exactly. So the mission of this deep dive is to understand why machine learning projects break before they even start.
Yeah, it's so common.
We are going to build an intuitive mental model of development environments. The goal here is to move you from like a beginner Python script.
Someone who just wants the code to run once.
Right, exactly. Move you to someone who thinks like a professional ML engineer where the code runs reliably everywhere, every time.
Yeah, and to fix environment drift, we first have to fundamentally change how we view our code. Beginners tend to conceptualize their Python script as this, independent, standalone entity.
Like the script is the entire universe.
Exactly. But your machine learning code does not run in a vacuum. It runs inside a highly specific, highly controlled execution environment.
Okay, so if I am picturing that environment, I'm guessing it's not just the Python language itself, right? It has to be an entire ecosystem.
Oh, absolutely.
Like you have the exact version of Python, the specific versions of every single library your code touches, the underlying system configurations of your operating system.
Yes, and even the hidden execution paths your computer uses to locate those tools.
Right, so if any single one of those variables shifts, the behavior of your code shifts.
And in the realm of machine learning, those shifts are uniquely catastrophic.
How so? Like worse than regular software?
Much worse. I mean, standard web development or, simple automation scripting, they have dependencies. But machine learning relies on massive, incredibly deep dependency chains.
Right, all those math libraries.
Yeah, you're dealing with rapid library updates where the mathematics itself might be optimized differently from one month to the next, right down at the hardware level.
Wait, really? A hidden numerical change? That sounds terrifying.
It is.
Because if I'm writing a standard app, an error usually means a crash. Are you saying in machine learning the environment can change the actual math without even telling me?
That happens way more often than you might think.
Yep.
Take something like a BELA backend.
What's that?
BELA stands for Basic Linear Algebra Subprograms. It's the underlying software layer that handles the incredibly heavy matrix multiplication required for neural networks.
Okay, the heavy lifting.
Right. If you run your code on a system with a different BELA backend, or even just a processor that handles floating point rounding slightly differently.
You get different math.
Exactly. You get variations in your numerical results. A slightly different version of PyTorch might compile its computational graph in a new way, and suddenly the entire predictive output of your model drifts.
Oh.
It's not just that the code crashes. It's that the code runs perfectly fine, but silently gives you the wrong answers.
That makes me think of running ML code like baking a highly delicate souffle.
Oh, I like that.
Right. You can have the exact same recipe, which represents your game, but if you take that recipe to a completely different kitchen and you use a slightly different brand of flour.
Or an oven that runs just 5 degrees hotter.
Exactly. Due to its internal thermostat, which represents your environment, the whole thing completely collapses.
It deflates, yeah.
The recipe alone is useless. You literally have to control the entire kitchen.
Controlling the kitchen is the perfect way to visualize it. In professional machine learning engineering, reproducibility equals environment control. If you cannot perfectly recreate the environment, You simply cannot trust the results of your model.
Wow, that's a powerful rule. Well, we don't just discuss theory here, right? We want you to build alongside us. So to lock in this concept, let's look at today's mini project.
Let's do it.
We are calling it OS Automator. It's a tool designed to organize and manage ML datasets. And our goal today isn't to write the complex logic of the dataset parsing itself.
Right, no heavy logic yet.
Yeah, we just want to give this tool a clean, professional foundation before a single line of logic is written.
It's like setting up the construction site before pouring the concrete.
Mm-hmm.
When you open your terminal to start a project like this, the first thing you do is create a root folder. MKDR Osimator and CDOS Automator.
Sure, the basic holder.
But inside that root folder, professional engineers establish a very specific architectural structure. You need a dedicated folder for your raw and processed datasets, typically called data.
Okay.
You need a CRC folder, which stands for source, for your actual logic. You need a notebooks folder for your exploratory data analysis.
Right.
And finally, a main.py file to tie it all together at the root level.
So as a beginner, my immediate instinct is to just throw absolutely everything, like all my messy Jupyter notebooks, my Python scripts, and my raw CSV datasets into one big folder.
It's your giant junk drawer approach.
Yeah. Just so I can find them easily, It's all right there in front of me. Why go through the hassle of separating everything into CCC and notebooks?
Well, mixing everything together is a guaranteed path to technical debt as a project scales.
Really?
Oh yeah. Beginners use a single folder as a junk drawer. Professionals separate their concerns because of how code moves into the real world.
How so?
Well, the SRC folder is particularly critical. Separating your core logic from your scratchpad experimental notebooks allows you to actually package your code.
Oh, I see.
Yeah, you can reuse it across different parts of the project and scale it for a server deployment later. Your notebooks are just for playing around and visualizing data. Your SRC folder is the serious, reliable engineering logic that gets deployed to production.
Right. It's the difference between doodling on a napkin and drafting an actual architectural blueprint.
Exactly.
You wouldn't hand a builder a napkin with coffee stains on it.
I hope not.
So to build this professional structure, we really have to adopt an engineer mindset. And a huge part of that is stepping away from the graphical user interface. We aren't clicking folder icons to make these directories.
No, definitely not. Real ML engineers live in the terminal. The command line is where you run data pipelines, debug tricky hardware integrations, and install dependencies.
Using core commands like pwd, ls, and cd.
Exactly. While we won't walk through every single keystroke today, the mindset shift is understanding that the terminal is your direct line of communication with the operating system.
But the terminal also presents this massive, dangerous trap for beginners. I'm thinking of the global Python problem.
Oh, man. The single biggest mistake a new developer can make.
Right.
If you open your terminal and simply instruct the system to pip install a package like NumPy or Pandas, the computer defaults to installing those libraries globally.
Just right onto the whole machine.
Yep, it attaches them to the main system Python installation that your entire operating system relies on.
To bring back my kitchen analogy from earlier, installing globally is like having a massive shared apartment building kitchen for every single resident in the building.
That sounds like a nightmare.
It is. Project A is cooking a roast and needs the oven set to 350 degrees, which, relies on NumPy version 1.21.
Okay.
But Project B is baking bread and cranks the oven to 400 degrees, relying on NumPy 2.0. If they share one single global kitchen, they are constantly ruining each other's dinner.
That is perfectly put.
Right. A global install guarantees an entirely unpredictable system because your projects are fighting over the exact same resources.
And it actually goes even deeper than your own project's fighting.
Wait, really?
Yeah, your computer's operating system itself uses that global Python installation for its own internal background tasks.
Oh, no.
Yeah. If you forcefully upgrade a library globally to serve your new machine learning project, you might accidentally break a core system utility that relies on the older version of that same library.
That's terrifying. So you aren't just breaking your projects, you risk destabilizing your actual machine.
Exactly.
Okay, so we desperately need a way to stop sharing the kitchen. I'm deducing the solution is giving every single project its own private, isolated space.
You got it.
And in the Python ecosystem, we call this a virtual environment. But I want to understand the actual mechanism here.
Sure.
When I issue the command in my terminal to create a virtual environment, like python-m venv, What is actually happening on my hard drive?
Good question.
Is it downloading a massive 3 GB duplicate copy of the entire Python language software every single time I start a new project?
See, that is the assumption most people make, but
Hmm.
it reveals what we call the shim reality.
The shim reality.
Yeah, virtual environments are not full duplicate installations. They're not magic.
Yeah.
They work in a much lighter, more clever way by simply manipulating your operating system's path variable.
The path variable. Okay, if you have never encountered this concept, think of the path variable as your computer's internal VIP list.
A VIP list, I like that.
Right. It's a text list of folders that the operating system checks from top to bottom whenever you type a command.
And that introduces the concept of path precedence. Your system searches for executable files in a very strict order.
Right.
When you type Python into the terminal, the OS runs down that VIP list looking for the first folder that contains a program named Python.
Okay, that makes sense.
Normally, it finds the global installation.
Yeah.
But when you create and activate a virtual environment,
Which you do by typing source, then by activate on Mac or Linux, right?
Yeah.
Or ven scripts activate for Windows.
exactly. When you run that, you are essentially shoving the path to your project's local, hidden folder to the very front of that VIP line.
Oh, so you basically bribe the bouncer.
You bribe the bouncer.
The computer looks at the top of the list, sees your local project folder first, finds the local Python executor there, and immediately stops searching.
Yeah.
It never even looks at the global system. It's like a set of blinders for your operating system.
And those blinders are entirely temporary. Understanding this path precedence explains one of the most incredibly frustrating beginner traps in all of software engineering.
Oh, I think I know what's coming.
The hidden interpreter trap.
I have lived this trap. It's awful.
We all have.
You do everything perfectly. You create your virtual environment, you activate it, you install your specific versions of NumPy and Pandas, your code is running beautifully.
Everything is great, right?
But then you want to keep that terminal window open to monitor a training loop, so you open a second brand new terminal window to run a quick test script.
Uh-oh.
You type python main.py, and suddenly the screen lights up red with a module not founder. No module named NumPy. And you end up staring at the screen screaming, I just installed it 5 minutes ago.
It's so frustrating, but the reason it fails is because that second terminal window has absolutely no idea your virtual environment exists.
Right, because of the blinders.
Exactly. The path variable modification, those blinders we just talked about, is strictly limited to the specific terminal session where you ran the activation command.
Oh, wow.
When you open the second window, it defaulted back to the standard global VIP list.
It is exactly like having the right key in your hand, but you walked down the hall and tried to open the wrong door.
That's exactly what it is.
You have the perfect environment built and fully stocked, but this new terminal window is looking at the global system, which doesn't have your specific machine learning libraries installed.
Which brings us to the most important debugging skill you can develop.
What's that?
Whenever you encounter a missing library error, never assume you are in the right place. You must verify your environment.
How do you do that?
You literally ask the operating system, which Python are you currently using? By typing which Python on Mac and Linux, or where Python on Windows.
Okay, so when I hit enter on that verification command, what exactly is the output telling me?
You are looking for a long, specific file path. The expected output should point directly inside your project directory.
Okay.
It should look something like pathatorios automator ved python. If the terminal spits out a short, generic system path, like a script in Python, you immediately know you are outside the protective bubble of your virtual environment. You are using the wrong interpreter.
Verifying the interpreter path is an absolute lifesaver. Okay, so let's say I have successfully isolated my environment, I avoided the hidden interpreter trap, and I have installed all my libraries into this private bubble.
Perfect.
How do I actually track what I've installed? Like, if I want to hand this OS Automator project over to a colleague or deploy it to a cloud server, how do I ensure they get the exact same kitchen setup?
Well, the standard mechanism is generating a text file that lists every single library and its exact version number.
The requirements.txt file.
Beginners usually just run a simple command, pip freeze requirements.txt, to freeze everything currently installed in their environment and dump it into that file.
And isn't that the end of the story?
For a tiny personal script, that is acceptable. But professional industry workflows go much further because dumping everything creates a massive problem with bloat.
Ah, I can see how that happens. If I just freeze everything in my environment, aren't I also packing up all the messy development and testing tools I use?
Exactly.
Like the formatting tools, the syntax checkers, the local testing frameworks. None of those actually help the machine learning model make predictions.
You hit the nail on the head. In professional dependency management, we strictly separate dependencies into two distinct categories.
Okay, what are they?
First, you have production dependencies. These are the core libraries your code literally cannot function without, like NumPy, pandas, model libraries. These live in your main requirements.txt file.
Makes sense.
Second, you have development dependencies. These are the tools you use while writing and testing the code, like PyTest, linters, formatters. But they're completely unnecessary for running the finished application.
Right.
These belong in a separate file, typically named requirements-dev.txt.
But why does this separation matter so much once the code leaves my laptop? I mean, if the server has a little extra storage space, why not just send all the development tools over anyway?
Because in an industry environment, keeping production lightweight is crucial. When you deploy a modern ML framework like PyTorch or scikit-learn, they break easily with mismatched environments.
Okay.
Plus, if you bundle it into a Docker container, every single extra library increases the size of that container. Yeah. Larger containers take longer to boot up, which costs money and slows down response times.
Oh, I hadn't thought about the cost.
And even more critically, extra libraries expand your attack surface.
Security vulnerabilities. Hacker targets.
Precisely. If a development testing framework has a known security flaw, and you accidentally deploy that framework to your live production server because you didn't separate your requirements files.
A hacker could exploit that testing tool.
Yep, and gain access to your proprietary machine learning models or even customer data. You want the production environment to be as lean and locked down as mathematically possible.
Wow, this explains why the actual industry workflow is so incredibly rigid. A professional doesn't just start coding.
Not at all.
The sequence looks like this, right? First, you clone a repository from your version control system. Second, you immediately create your isolated virtual environment.
Yes.
Third, you install the exact dependencies from that lean requirements.txt file. Fourth, you verify the environment is active by checking the Python path. And only then do you actually attempt to run the machine learning pipeline.
Notice how early in that sequence the environment is established. If step 2 fails, if your environment is corrupted or dependencies clash, the entire system fails gracefully before anything runs.
Right.
You don't even get to the machine learning part, which is exactly how it should be.
This entire workflow really highlights some of the most common painful mistakes beginners make.
So many.
Using the global Python installation, ignoring the activation step and falling into the hidden interpreter trap, failing to verify the path when things go wrong, mixing production and development dependencies into one bloated file.
And, well, we have to mention the ultimate sin.
Pushing your actual Venn folder to GitHub?
Yes. You must never, ever push the virtual environment folder to a shared version control repository.
Because that folder is basically a giant box of operating system-specific puzzle pieces, right?
That's a good way to put it.
If I build an environment on my Mac, the virtual environment folder is filled with Mac-specific executable files.
Right.
If I push that entire folder to GitHub and you download it onto your Windows machine, it is completely useless to you. Windows cannot run Mac executables.
Nope.
Plus, it bloats the repository with tens of thousands of files that just don't need to be tracked.
Exactly. You share the recipe, which is the requirements.txt file, not the entire kitchen.
Yeah.
The environment itself is meant to be completely disposable.
Throw it away and build a new one.
Yep. It's designed to be rebuilt dynamically from scratch on whatever new machine downloads the repository.
And to ensure you never accidentally push that massive folder to GitHub, this is where a .gigignore file becomes your absolute best friend.
Highly recommend it.
A .gitignore is simply a hidden text file in your project folder where you write down the names of things you want your version control system to be completely blind to. You literally just type the name of your virtual environment folder, usually venvav, into that text file, and Git will pretend the folder doesn't even exist.
It acts as an invisible shield.
Exactly, protecting your repository from all that localized bloat.
That is a critical piece of the structural foundation. A well-configured .gitignore is truly the hallmark of a professional repository.
Well, we have covered a tremendous amount of ground today, moving from the microscopic fragility of machine learning hardware optimizations to the macro architecture of path, precedence, and dependency separation.
It's a lot, but it's essential.
Let's recap with an engineering checklist for you, the listener. Think of this as a locked segment to make absolutely sure your foundation is rock solid before you write a single line of data science logic.
First on the checklist is isolation. Have you added your Venn folder to your .gitignore file so it acts as that invisible shield against GitHub? Second is reproducibility. Have you separated your development tools and created a lean production-ready requirements.txt file?
Third is verification. Did you actually run the which Python command to check your Python path, proving to yourself that you were safely inside the protected bubble of your virtual environment?
Always verify.
And finally, structure. Do your SRC and data folders exist, properly separating your core engineering logic from your messy experimental data?
If you can check all 4 of those boxes, you are no longer just a scripter. You are operating at a professional engineering baseline.
That's a great feeling.
But understanding the theory isn't enough.
Yeah.
I want to challenge you to a micro exercise.
Oh, homework.
A fun one. Go to your computer and actually build this OS Automator project structure. Set up the virtual environment, install a library like NumPy, and save the requirements file.
And then we want you to intentionally destroy it.
Break it on purpose. Write a tiny Python script that imports NumPy and prints a simple message, then deactivate your virtual environment so you are back in the global space. Try to run your script and watch it violently fail. Experience that red text on purpose. Analyze what the terminal is telling you.
Desensitize yourself to it.
Exactly. Then reactivate the environment, verify the path, run the script again, and watch it succeed.
I absolutely love that approach. Break your environment on purpose in a controlled setting so you aren't terrified of the error messages when they inevitably happen by accident in the real world.
They will happen.
The ultimate takeaway from all the engineering sources we analyzed today is this. Most machine learning systems out there in the real world do not fail because the neural network architecture is poorly designed or the mathematics are flawed.
No, they fail before the math even starts.
Because of bad environment engineering.
Environment drift is the silent killer of data science. But now that your mental model of the operating system is stable, we can move forward into the code itself.
What's next?
Well, now that your system is stable, in our next lecture, we'll dive into how Python actually stores and manages data in memory.
Oh, getting deeper.
Yeah, because this is where silent bugs begin and where real engineers start thinking differently.
That is going to be a fascinating transition from the external environment to the internal memory management. Until then, I want to leave you with a final thought to ponder on your own.
Let's hear it.
We started this deep dive talking about the NumPy 2.0 disaster. A single software library updating over the course of just 1 year can completely shatter a complex application if the environment isn't strictly controlled.
It's true.
So if our software environments are this incredibly fragile to tiny changes in a library version over just a single year, how do we ensure the massive, complex AI models making critical decisions in the world today will still function safely in exactly the same way 5 or 10 years from now?
It's a huge question.
Something to think about. Keep your environments clean, build your foundation strong, and we'll see you next time.